So let's continue the journey about nonstationary time series analysis with manifold learning techniques. And today we will talk about a very specific topic that is called Roseland. And this is an algorithm that can be viewed as Roseland. That can be viewed as a variation of diffusion map. And we have talked about diffusion map in the previous lectures. And if you haven't learned diffusion map, you may want to go back to take a look. And the main focus of this Roseland algorithm is trying to speed up diffusion map. So first, what is the limitation of diffusion map? Well, there are many limitations for sure, but one of the main limitations when we apply it to real data is when we have a big and noisy data set. Okay, why? If you have a big data set, then eigendecomposition is usually expensive. And if you remember, the complexity of eigendecomposition is usually n raised to power of log 27. So it is kind of n raised to power 2.81 or something, which is almost impossible when data is large. In your MATLAB, in your small computer, you can try eigendecomposition when the matrix size is like just 10,000 by 10,000, then you will start to feel terrible. But what about if you have million by million data? You have data set with million points, then that is kind of impossible. Well, there are solutions for sure. Otherwise, the first solution is to say, hey, how about if we try to make the matrix to be sparse? Make it to be sparse. That is good. And how to sparsify the matrix so that we can speed up the computation? You can say, okay, let's use KNN, nearest neighbors, or use epsilon bow, nearest neighbors, to construct the graph and the graph Laplacian. And if you remember, when we introduced diffusion map, we have mentioned several different ways to construct graph Laplacian. And the KNN, k-nearest neighbor, and epsilon bow techniques are two commonly applied ones. Okay, yes, you can make it sparse, but this approach is only good if the data is clean. And certainly you have theoretical support. Or another thing is, you can try, okay, how about nice strong extension? That is, we downsample the data. For example, we have originally 1 million points, and now we only take 1,000 subsample points out of it, out of 1 million, and we run the algorithm first, and then we do extrapolation. This is called nice strong extension. Well, this approach is good for spectral clustering, because in spectral clustering, we only need to recover the first few eigenvectors. But we will lose some geometric details because we need higher order eigenvectors and eigenvalues to recover the geometry. So these two methods, well, this one sounds good. This one has some limitation. But is this really good in the end? Not really. This one, actually, the nearest neighbors is not robust to noise. That is, if you have noise, the data is noisy, then finding nearest neighbors is challenging. In some applications, you do have nearest neighbors information in the very beginning, then good, you can use KNN, you can use this sparsity. But what about if you do not have this information and you need to determine the neighbors, but the data is noisy? Then you run into trouble. Why? If you look at this example, you have xi tilde, that is the noisy data. That is the xi plus xi. Xi is the clean data you have interest. Xi is the noise. And let's make an assumption that data and the noise are independent so that we can do calculation easily, okay? Now you see, xi tilde minus xj tilde, that is usually the way we can use if the data is saved in the Euclidean space. And we want to evaluate the L2 distance, and you can just do a simple calculation and see that this L2 distance of the noisy data is the L2 distance of clean data plus L2 distance of noise, pure noise, plus the inner product of data and the noise. Now what you can see from here, actually if you do some calculation, you will see that this guy is a non-central chi-square distribution, and how to appreciate it, you can just see it from here. Suppose you have Ci that is just IID noise, okay, and the Gaussian, then this guy actually follows 2 chi-square p. And you know the basic property of chi-square p. Its mean is p, standard deviation is square root of p. Okay, and what does it mean? It means that when p is large, then all the L2 distance of Ci minus Cj squared will be centered at 2 times p with a very, very small square root of p standard deviation. So that you just get this p value that may dominate the information we have interest, xi minus xj. And this is a very typical high-dimensional probability structure. That is, if you have a high-dimensional random noise, actually the point will somehow looks like supported on a high-dimensional sphere. Okay, that is that kind of concentration property. So if you use the usual L2 distance, then you may very easily find wrong neighbors. Because what you have interest is this guy, but the noise will come into play and the may dominate the true information. So the neighbors you find is wrong. Okay, and the limitation of Nystrom is, I have mentioned, you will lose geometric information. So our question here is, we want to use diffusion map when the data is big and noisy, but we run into a very essential challenge, that is the computational limitation. How can we speed it up? And also maybe simultaneously solve these 2 problems. Can we do it? Well, suppose we can remove these two limitations, then it's good, isn't it? Can we? The answer is yes, we may be able to do it. And our solution is take the diffusion into account. But when we do diffusion, we will consider something called landmarks. Okay, what does it mean? If you remember in our diffusion maps lecture, we say that in diffusion map, we use the diffusion property to consider how the points diffuse from one point to another, right? And in diffusion map, if we consider diffusion from xi to xj, the diffusion is just directly from xi to xj. There's no constraint. Well, there's a geometric constraint for sure, but we will not put any other limitations. But what about now? We say, hey, when you want to diffuse from one point to another, I want to set up some constraints, or we call them landmark sets. We will choose some points as landmark set. And how to choose the landmark set is important, and we will come back to this issue later. This is actually very, very important. Okay, but at this moment you just say, oh, we have a landmark set. The landmark set is called Y. Okay, then when we run the diffusion, when we want to diffuse from xi to xj, we say, hey, you no matter what need to diffuse from xi to y first, and then after you arrive at y, then you diffuse to xj. That is, you split the diffusion from xi to xj into 2 steps. First, you have to diffuse 2 different landmarks and then go back to xj. And we claim that by controlling the diffusion in this way, we can speed up the computation and get what we want to get. Okay, so this is actually an algorithm called Roseland. Okay, which Roseland stands for robust and scalable landmark diffusion. An algorithm is very simple. You can finish the algorithm, you can write the code in MATLAB just by 10 lines. Just 10 lines, very easy. Okay, and there are technically 4 steps, just 4 steps. The first step is you will construct a tall and a thin matrix called WR, and the M here is the number of landmarks you choose. Okay, and N is the number of points xi from x1 to xn. And we will put WR, ij, the ij's entry, to be the distance in between xi and xj squared divided by epsilon. Epsilon is the bandwidth. And as we mentioned in the diffusion map algorithm, this bandwidth epsilon plays a similar role as the bandwidth in diffusion map. We will discuss how to choose epsilon later. But right now you can choose epsilon to be a median of pairwise distances in between xi and yj. And later on we will discuss how to choose epsilon. So this matrix will describe affinities between data and landmarks. So what you have right now is this guy. We have WR, okay, which is a tall and the thin matrix. This is N by M. Okay? Very simple. Then we go to the second step. Doesn't work? Okay. Then we go to the second step. The second step is you have WR times WR outer product. You have outer product WR itself. Sorry, WR transpose. And we denote this guy as W. And what is the size of W? As you can imagine, because W is WR outer product R itself, this is a matrix of size n by n. So this is a big matrix. W is a big matrix. And what you do is, you will do a row sum. You multiply by 1, and this one is a vector with all entries 1. So this indicates you evaluate the row sum of all entries, all of this W matrix. And you pick up the ith entry of the final row sum vector, and you put it in D matrix, which is DII. And this DII is actually the degree matrix associated with the affinity matrix W. So you have DII, and you remember in the diffusion map, you have to construct a degree matrix called D, and this is the degree matrix. And the physiological meaning or physical meaning of WR transpose is the description of affinities among data points, because WR transpose means that you will have, this is this guy, right? So what you do is you will have jump from the data point to one landmark point, and from the one landmark point jump to another data point. That is from xi to xj. That is the meaning of this W matrix entry. So that describes the affinities among data points. Okay, and then what you do is you will run singular value decomposition of this D minus half WR matrix. And why do we want to do so? The reason is very simple. If you remember in diffusion map, what we did was evaluating the eigendecomposition of D inverse W, the transition matrix, right? And right now we have this W as the affinity matrix of the original data set of xi up to xn, and we have constructed degree matrix D using this affinity. So D inverse W is actually what we want from the diffusion map algorithm. And we can see that this D inverse W matrix is similar to D minus half WR transpose D minus half, assuming that D is non-singular. which is usually the case. Then once you get this guy, you see that it is nothing but the outer product of D minus half WR. Right? So you just need to calculate the SVD of D minus half WR so that you can get the eigendecomposition of the inverse W. So you somehow can recover the diffusion map using this Roseland using these landmarks. And then finally, you just calculate W bar to be D minus half U, which is nothing but like what we did before in diffusion map, right? You calculate a eigendecomposition of a symmetric matrix, but what you want is the inverse W, so you just move it back by multiplying D minus half U. And that is the final eigenvectors we have interest. And by combining the singular value, and you know, once you have singular value, you take square, then you get eigenvalues of the inverse W. And you have U bar, which is the eigenvectors. So we can just consider the similar embedding procedure like before in diffusion map. We just embed each point by SL 2 times T. 2 square, this is, you take square to recover the eigenvalue, and the T is the diffusion time, and you use the UL bar, which is the L's eigenvector of U bar, and then you get a point in the in the lower dimensional space. Well, and we call this guy the Roseland embedding with time. And then you can also define Roseland diffusion distance and so on. And the notations are put here. So this is overall the Roseland algorithm, very simple. And in the next lecture, we will talk about its theoretical properties. But right now, let's take a look at its benefit, at least on the intuitive level, and some numerical results. First, the consequence. You somehow feel the benefits of the previously mentioned KNN and epsilon sparsity properties. This sparsity is actually replaced by landmarks. Right? You somehow make the matrix smaller instead of large. Second, well, you don't, and in particular, you don't need to find neighbors. There's no neighbor searching. So even if the noise is big, you don't need to worry. Second, you do not really run subsampling. You do run subsampling, but you also use the diffusion to conquer the subsampling procedure, and there is no extrapolation step. So you use actually all points. So somehow this nitron property is replaced by diffusion, so that you may have a better chance to preserve the geometric information and speed up the algorithm. And this is actually the computational complexity. If you remember, I give you a matrix of size n by m, and n is greater than m. Okay, then running the singular value decomposition, the computational complexity is n times m squared. So suppose m is n raised to power beta, and usually beta is less than 1. Then Roseland algorithm will have the computational complexity n raised to power 1 plus 2 beta. Okay? And in diffusion map, even if you use KNN with a sparsity, then existing theory tells us that the computational complexity is 2 plus epsilon. Epsilon is a small constant, and the implied constant will depend on epsilon. Certainly, the smaller epsilon is, the larger the implied constant is. So that is the order. And if you run nitron extension, suppose in nitron extension you take a subsample point of size n raised to power beta, then this is the computational complexity of nitron extension. So if you take this into account, then what you see is, suppose we choose beta to be slightly less than 1/2, just like square root. Then you see that this computational complexity is already smaller than diffusion map algorithm. And with this kind of very basic calculation, you see that, well, usually we can choose beta to be held or something, and we can get somehow quite nice result when n is large. And you may question, what about if n is small? Well, if n is small, then this is maybe probably not a very good approach, because don't forget, this algorithm is developed when n is large. And when n is small, for example, you have just 100 points. Then you take square root, you just have 10 points. Now why do you want to consider this algorithm, right? 100 points, you can easily handle it. So usually, maybe if you ask me for some recommendation, I would say if n is greater than 5,000, then maybe you can start to consider Roseland. But if it is just 1,000, well, you can still use it, but maybe the benefit is not so strong. And if n is actually 1 million, ambient space dimension is 300, beta is 0.45, then in this small computer, it only takes about 3 minutes to finish the computation. So it can allow us to go beyond 1 million to some extent. And we need to mention that there exist several landmark-based approaches close to this algorithm. For example, back in 2014, there was an algorithm also used landmark idea reference set to speed up algorithm, but they use a very different normalization algorithm, normalization to design an algorithm so that the diffusion property is not preserved. And later on, I will show you the importance of preserving the diffusion property. If you don't preserve the diffusion, then the result is actually not as good. And also they do not have theoretical results to our knowledge. And there are many, many papers actually using this landmark idea to do spectral cluster. Okay, and but again, there is no theoretical analysis. And we will talk about some theoretical analysis of Roseland later. Okay, so this is a simulation. And the simulation is very simple. You just take S1, okay, and you just uniform sample from it. There is no density issue, no non-uniform density issue, and you just add noise. And now we take 90,000 points, and the beta is 0.5. And you run it. Now what you get is this guy. I only show you the eigenvectors. The top one is using the traditional Nystrom extension. This HKC is the paper I mentioned before. They use a different normalization so that they do not have do not preserve the diffusion property, and this is the Roseland. And what you see here, the top 3 rows are the first 5 non-trivial eigenvectors. And the bottom 3 rows are the 6th to 10th eigenvectors. What do you see here? The interesting fact is, if you use Nystrom extension, you can recover up to the 7th eigenvector, and starting from the 8th, you don't see too much. But if you use Roseland, you can recover up to 9 eigenvectors, which is a good sign because it means that we can get more geometric information. You use HKC, yes, you can also recover 2 9s. And what is the difference? The difference is actually the phase information hidden inside the eigenvectors. So, you see, there's an obvious difference, right? And now how about if we try to do embedding? For example, we want to recover the manifold. This is usually what we like, right? You use Nystrom extension, the first 2 eigenvectors, yes, you can get S1 recovered. Use HKC, you can also get it recovered. Using Roseland, well, it is also recovered, but you can see an immediate difference, isn't it? This one is kind of sharper compared with these 2. And how about if we take a closer look in between HKC and the Roseland? You will see that this is the Nystrom compared with Roseland. This is HKC compared with Roseland. And what I plot here is at each point, I just after embedding, I evaluate this norm. I evaluate this point, each point, embedded points norm. That is, we have V1. Suppose we have V1 and V2. or these are top two eigenvectors evaluated from either Roseland, Nystrom, or HKC. And what we plot on the right lower part is this following thing: I squared plus V2 I squared. This is called AI. This is the amplitude of the embedding. This is the amplitude of embedding. Then, if you take a closer look, you will see that the amplitude of embedding using HKC is much it fluctuates much more compared with using using Roseland. Okay, so that somehow shows you the benefit of doing the diffusion in the correct way. Okay, and then this is a benchmark result, and this MNIST database is kind of very commonly widely used database. It contains 70,000 images. Looks like this one, and we did two examples. One is the original one that is clean, and then we add some noise so that you see noisy data on the right hand side. And this is the computational time. You can run PCA directly, only takes 4 seconds. But if you use diffusion map, yes, we try to find go to a larger computer, and we can finish it. Take 1,400 seconds, which is quite slow. And now if we take beta at 0.5, using Roseland, it is 15 seconds. Using Nystrom, it's 4 seconds. And there's another algorithm, that we were asked to compare, and I will not introduce it. It takes 300 seconds to finish. Okay, if you have interest, you can go to the paper. We have written the detail about this algorithm. And then what we do is, after the embedding, we try to determine if we can better classify or identify the number from the handwriting. Then we just use the very basic quantification that people use and report the accuracy. Now let's take a look at the result. We use the whole MNIST data set, 70,000 images, and suppose beta is 0.3, beta 0.4, and 0.5, different numbers, right? You can see that the diffusion map is here. Okay, diffusion map is here, which can go up to almost like 0.85, which is good. Okay, so this is clean data. We don't add any noise. And now you compare with Roseland. Roseland, even when beta is 0.3, is already better than using Nystrom, which is here, and LLL. And for LLL, we have optimized it. Okay, and the Nystrom have all is standard. Okay, so you can already see, and PCA is here. PCA is here, which you can see PCA does have some benefit, but not too much. Okay. Now, if you go up to 0.4, you can see that Roseland start to catch up with diffusion map. But the other algorithms like Nystrom or LLL, they do not really improve too much, and the PCA is the same, always the same here. Doesn't matter, right? And if we go up to 0.5, then you can see that diffusion map and Roseland, their performance are almost equivalent. Almost equivalent. There's no difference. Okay, so this tells us that, well, using Roseland, you can achieve almost similar performance compared with the original diffusion map when data is clean. What about if data is noisy? You can see this gap, right? You can see this gap. This gap is obvious. Now you can see when data is noisy, and you play the same game. What you see here is, first, the diffusion map performance has decreased. It decreased from 0.85 to 0.8. Okay, and all the other performances are somehow decreased as well. And you can also see a gap here. And you may say, oh, look, in this case, Roseland starts to fail. But don't forget, this, if you take beta 0.3, actually you have very, very few points. Right? Take a 70,000 and 0.3 power, you see how few landmarks are. So you actually lose quite a lot of information. But when beta is 0.4, suddenly you see Roseland starts to improve and almost catches up with diffusion map. And interesting enough, when beta is 0.5, we found that diffusion maps, Roseland seems to kind of outperform diffusion map. And why so? One reason is we believe is because of the denoising property, but there are several open questions remain unsolved, so we cannot make a conclusion. This is just an observation, which means maybe some kind of combination of downsampling and these diffusion properties can give us something good. Okay, but this already gives us some evidence that the Roseland does play a role, does have benefits. Okay. Now we can see a final application, that is image segmentation. So for example, in these images, the first one is a cameraman, the second one is a hawk, and this is the image size. And here we 8 noise as before, 8 noise as before. And what we do here is we want to do image segmentation. And the usual procedure is we truncate the picture into several 5 by 5 pitches, overlapping for sure. Every pixel will be attached with a 5 by 5 pixel. That is very, what it means is you have an image. An image can be viewed as a matrix, right? And for every pixel here, what we do is we take a 5 by 5 patch. And what is 5 by 5 patch? We use a center at this point, a 5 by 5. This is a patch. This is 5 by 5 patch, centered at 1 pixel. And for every pixel, we have one 5 by 5 patch. So in total, we get 155,000 patches in 25-dimensional Euclidean space. And then we run spatial clustering. And that is the kind of image segmentation basic algorithm. There are a lot you can do. And right now, these approaches may be in image processing. I believe using this CNN approach is much better. But anyways, this is a benchmark to show you how it works, how it performs. So this is the result, segmentation if data is clean, and you just run different algorithms. And it is actually not that easy to say which one is better, but I just want to show you the picture. And using Roseland is very fast. You can just get it without worrying too much. And we can only run Nystrom. It is not possible to run diffusion map. It's too large. Okay, and this is when data is noisy, and you can see that there's some kind of confusion here, but the confusion is less dramatic. Okay, and this is the whole result for image segmentation. I think overall performance of Roseland is not too bad, and you can see what's going on. Okay, this is the final result. Okay, this is something we will talk in detail later. And this is the arterial blood pressure signal. Okay, and we try to visualize this arterial blood pressure signal over 10 hours. This is a surgery lasting for 10 hours. Actually, this is a whole liver transplant surgery. And in total, you get that many 120,000 points, and the beta 0.48, and you just need about 10 seconds to get the embedding. And this embedding, each point represents one cardiac cycle. Each one cardiac cycle will be represented as a point. And this thick line is the median trajectory. And we will introduce details about how to do calculation and use this embedding later. But this is the plot that tells you the dynamics of your hemodynamics. And you can see that if I plot it using 3-dimensional video, you can see there are a lot of strange structure at different time. The color indicates time. And there are several interesting features that we can explore. And these are the references, and this is the method code. And this is more applied one, this is more theoretical one, and we will discuss some theory underlying diffusion Roseland in the later lecture. Thank you.